So here is the video answer key for chapter 6. Determine whether each table demonstrates a linear, quadratic, or exponential relationship. If it is exponential, state whether it is exponential growth or exponential decay. Find the function. So when I look at letter A, the first thing I need to realize is that it looks like this is going to be exponential. So let's double check that this is exponential. If I take 2.25 divide by 3, divide by the number above it, I get 0.75. If I take 1.6875 divide by 2.25, I get 0.75. If I continue this down, 1.6875, rephrase that, 1.2656 divided by 1.6875, I get about 0.75. If I take 0.94922 and divide by 1.2656, I get about 0.75. So this is division. So this is going to be exponential. My successive quotient here is less than 1, so it's exponential decay. So my equation is y is equal to my a is y when x is 0. So that's 3 times my b, which is 0.75 to the x power. Letter B. Having this 0 here tells me more than likely division's not going to work. Negative 1 divided by 0 doesn't work. 0 divided by negative 1 is going to be 0. So division's not going to work. This is going to be some sort of linear or quadratic. Negative 1 minus 0 is negative 1. 0 minus a negative 1 is 1. 3 minus 0 is 3. 8 minus 3 is 5. So it's not exponential. It's not linear. Let's see if it's quadratic. 1 minus a negative 1 is 2. 3 minus 1 is 2. 5 minus 3 is 2. So this has to be quadratic. My a is half the second difference, so my a is 1. My c, so this is quadratic. Y is equal to a is 1, x squared. My c is y when x is 0, so my c is 0, so I could put plus 0 if I wanted to. My b is my first difference is equal to a, which is 1, plus b. Subtract 1. I get b to equal negative 2. And c, again, is 0, so if I could put plus 0, I can. But there's my answer. Okay, let's try letter C. Over here, if I do my differences, 6 minus 2 is 4. 18 minus 6 is going to be 14. 54 minus 18, oh my goodness, I don't think this is going to work. 54 minus 18 is going to be 36. If I try my second differences, this is going to be 10. This is going to be 22. This is not linear. This is not quadratic. So let's go back and let's see if this is exponential. 6 divided by 2 is 3. 18 divided by 6 is 3. 54 divided by 18 is 3. 162 divided by 54 is 3. So this is exponential. Since my successive quotient is greater than 1, that's exponential growth. So then my equation is y is equal to my a is y when x is 0. Y is equal to 2 times my b is the successive quotient. My common multiplier b is 3 to the x power. Letter D, if I look at this, negative 4, negative 3.5, negative 3, negative 2.5, negative 2, it's going up by the same amount. So my difference Negative 3.5 minus a negative 4 is 0.5. Negative 3 minus a negative 3.5 is 0.5. Negative 2 minus a negative 3 is 0.5. Negative 2 minus a negative 2.5 is 0.5. So this has to be linear. Y is equal to my first difference, 0.5x minus 4, because my b is y when x is 0. Letter E, if I look at these, I can possibly notice that this is going down by half every time. 2 divided by 4 is 1/2. 1 divided by 2 is 1/2. 0.5 divided by 1 is 1/2. So this is division, 0.5 or 1/2. My successive quotient is the same. So this is exponential. Since this is 1/2, it's exponential decay. Y is equal to my A is y when x is 0. So that's 4 times my B is 0.5 or 1/2 to the x power. To the x power. This next one, again, 4 divided by 3, 3 divided by 4. My successive quotients don't look like they're going to be nice, so we're going to try differences. 4 minus 3 is 1. 3 minus 4 is a negative 1. 0 minus 3 is a negative 3. Negative 5 minus 0 is a negative 5. My first differences aren't the same. Try my second differences. Negative 1 minus 1 is negative 2. Negative 3 minus a negative 1 is negative 2. Negative 5 minus a negative 3 is negative 2. My second differences are the same, so this is quadratic. My second difference is negative 2, so that means that my A is negative 1x squared. My C, 3 is y is 3 when x is 0, so it's going to be plus 3. I need to find my b. My b is going to be, my first difference is 1 is equal to a plus b. My a is negative 1. Add 1 to both sides. I get 2 is equal to b. So this is plus 2x. There's my quadratic equation. Letter G. Letter G. Look at my numbers, 5, 10, 20, 40, 80. If I do my successive quotients, 10 divided by 5 is 2. 20 divided by 10 is 2. 40 divided by 20 is 2. 80 divided by 40 is 2. So this is going to be exponential. My successive quotient is greater than 1, so this is exponential growth. So y is equal to, that's an ugly y. Y is equal to, my y when x is 0 is 5 times my successive quotient 2 to the x power. Letter H. Because of all the decimals, I'm going to guess that this is going to be exponential. Let's double check. 0.75 divided by 0.5. I'm getting 1.5. 1.125 divided by 0.75. I'm getting 1.5. 1.6875 divided by 1.125. I'm getting 1.5. And lastly, 2.5313 divided by 1.6875. I'm getting about 1.5. So this is exponential. Since my successive quotient is greater than 1, it's exponential growth. Y is equal to, my A is y when x is 0, 0.5 times my successive quotient is 1.5 to the x power. All right. Exponential functions. Ryan bought a baseball card for $50. in 1995. This following table shows the value of the card. So this isn't population, this is actually value. Find the successive quotient. Okay, my successive quotient. First of all, remember 1995 is year 0. This is year 1, 2, 3, 4, and year 5. My successive quotient, 5250 divided by 50. I get 1.05. 55.13 divided by 5250. I get about 1.05. 5788 divided by 5513, I get about 1.05. 60.78 divided by 5788, I get about 1.05. 6381 divided by 6078, I get about 1.05. My successive quotient is 1.05. Write a function rule for the data. Okay, so this is exponential. It's exponential growth because 1.05 is greater than 1. So y is equal to, my initial value is 50 times 1.05 to the x power. Is the function exponential growth or decay? It's growth. Y. 1.05, my successive quotient, is greater than 1. Find the value of the car in the year 2006. 2006 minus 1995 is 11. I pull up my handy dandy calculator. I'm going to go ahead and plug this into my y equals 50 times 1.05 to the x power. I want the 11th year because 2006 minus 1995 is my 11th year. So 11 is $85.52. That's because x is equal to 11. In what year did the value of the car be over $80? Over $80. That looks like it's the 10th year because 81.44 would be over $80. The other way to find this is go to y equals, plug in $80 for y2. Make sure my window goes past that $80, so I'm going to have my y max go like to 100. I'm going to make my x max, make it 15. If I see the intersection, I can find it. Second trace to go to the calc menu. Number 5 is intersection. Enter 3 times. I get 9.6. And what year was the value over 80? Well, at 9 years, it's not over 80, but in 10 years, it's over 80. So I found the answer in either the table or in the intersection in the graph. But 10 years is not 10 years. It's the year 2005. I actually have to add it to this 1995. The number of miles of cable car truck, the number of miles of cable car truck during the late 1800s is shown in the following table. So let's try this again. The number of miles of cable car track during the late 1800s is shown in the following table. Again, the year that we're starting this, 1894 is year 0, 1, 2, 3, 4. This would be 5 years into it. I want to find my successive quotient. So I take 271.8 divide by 302, and I get 0.9. Take 244.62 and divide by 271.8. I get 0.9. Take 220.16 and divide by 244.62, and I get about 0.9. Take 198.14 and divide by 220.16, and I get about 9. Take 178.33 and divide by 198.14, and I get about 9.9. Find the successive quotient. It's 0.9, 9/10. Write a function rule for the data. That's going to be y is equal to my starting purchasing power. How about starting miles of track? Sorry about that. Is 302 times 0.9 to the x power. Is a function exponential growth to decay? It's decay. Why? Because my successive quotient is greater or less than 1, or we can say the amount of track is decreasing. Find the miles of track in 1900. The miles of track in 1900, pull up my handy dandy calculator, go to y equals, take out what I have in there, plug in my new equation, 302 times 0.9 to the x power. Okay. I want the track in 1900. This started in 1894, so 1900 minus 1894 is going to be 6. So I'm going to go to my table and find 6. 6 is 150.495 or 150.5. Excuse me, not 150. That's 160.5 miles of track. In what year would there be less than 20 miles of track left? So I want my y2 to be 20. Now, if I was in the table, could I scroll down until I get to 20 some here in y1? Sure, or below 20. Or I could plug it into y2. I want my window, 302 was my top number, so I need to see below 302. So I'm going to make this 305. And let's see, let's go past 15. Let's make this 25. That's a guess. Graph. There's my equation. Oh, I don't see the intersection. So I need to make my y's go past 25. Let's make it 45. See the intersection? I can find the intersection. 5, enter, enter, enter. 25.8. In what year would there be less than 20 miles? 25.8. I'm going to make that 26. So 1894 plus 26 would be 1920 would be the year. All right, let's go to the next page. Use transformation to describe the graph of each function as it relates to the function y equals 1.25 to the x. Okay. Remember, if I'm subtracting outside, this is a translation or a shift down 2 because it does exactly what it says. 0.25 multiplied in front tells me that I'm going to have a vertical compression since it's between 0 and 1. Plus 5 on the outside, this is going to be a translation or a shift up 5. multiply by 1.45 in front. This is a vertical stretch since it's greater than 1. For this one, I'm going to have a vertical compression and a shift down 6. It's compression because 1/3 is less than 1, and a shift down 6. And it's down 6 because it's -6. And finally, 4/3 is greater than 1, so this is a vertical stretch since it's greater than 1. And -3 is a shift down 3. Okay. Number 4. In each of these, the table represents y equals 1/2 to the x. Write the function rule that fits the transform data. Remember how these works. It's either going to be y equals 1/2 to the x plus or minus some number, or it's going to equal y equals 1/2 to the x. Excuse me. It's going to be y equals some number times 1/2 to the x. And I have to decide if it's adding or subtracting or multiplying by a number. So I'm going to go to my handy dandy calculator. I'm going to start off with what I know. Y is equal to 1, well, I'm going to put this in parentheses, 1/2 to the x power. See, it needs to be 1/2 to the x power. I'm going to make my table start at 0. So this is what the table should be, 1.5.25.125. Instead, it starts at 0.5.25.125. So it's decreasing by what looks like half every time. So that tells me that more than likely I'm not going to add or subtract. I'm going to multiply by something. So it's going to be y is equal to, well, what's it doing? It's decreasing by half. So it's 1/2 times 0.5 to the x. Double check this in my calculator. I'm guessing here, but I'm going to say that this is 0.5 times 1/2. I don't want the graph. I want the table. But do you see that this new table here matches what I already have, 0.5, 0.25, 0.125? So that tells me that my guess was correct, that my equation is y is equal to 0.5 times 1/2 to the x power. Let's try the next one again. This is what the graph should look like, 1.5, 0.25. But instead, I'm getting 2, 0.5, 0.25, 0.125. What's happening here? Am I adding by a certain amount? Am I subtracting by a certain amount? It looks like I'm doubling every time. So since it looks like I'm doubling every time, that means I think it's going to be multiplied by 2. So let's try 2 times 1/2 to the x. Again, I need to see the table, not the graph. 2, 1, 0.5, 0.25. This matches what I had in my original table. So I believe I was correct in saying I needed to multiply by 2 times 1/2 to the x. And then on the last one, I have 5, 4.5, 4.25, 4.125, 4.0625. Well, what's happening here? It doesn't seem like it's doubling or tripling. It looks like it's changing by some amount. It looks like 0.5, excuse me, it seems like the 1 is now 5. 0.5 is now 4.5. 0.25 is 4.25. 0.125 is 4.125. Do you see that it's increasing by 4? It looks like it's y is equal to 1/2 x plus 4, since if I did my differences, I would get 4. Well, excuse me, that's not right. My differences isn't there. My difference is from here to here, from here to here. That's where I'm getting a difference of 4. I'm comparing to what the table should be, even though this is what it is. So it should be plus 4. Let's double check to see if I'm correct in that. So I'm saying it's not multiplied by something in front. I'm saying I'm adding 4 to the back side. And again, I don't want the table. I don't want the graph. I want the table. But do you see that this table now matches the table? This table matches this table now. So I was correct in saying that it's y is equal to 1/2 times x plus 4. All right, let's continue. Undo what I just did. Okay. How much time do we have? Okay, we've done 26 minutes. All right. Complete the table. Let's complete the table. First of all, growth or decay 0.25 is less than 1, so this is decay. My initial value is the 50. Again, fill out the last column first. The factor is 0.25. The percentage is the difference from 1. So 1 minus 0.25 is 0.75. As a percentage is 75% decay. Next one, growth or decay, 1.9 is greater than 1, so it's growth. My initial value is the 4. In the parentheses, I have 1.9. The difference from 1 is 0.9, which is 90%. Move the decimal twice. Growth or decay, 0.6 is between 0 and 1, so this is decay. My initial value is the number in front of that, which is nothing, so it has to be the number 1. Fill out the last column first. In the parentheses is 0.6. The difference from 1 is 0.4. As a percentage, it's 40%. And if you need to, put the 0.9 over here, 90%, 0.75 over here, 75%. Next one, 1.45 is greater than 1, so this is growth. My initial value is the 0.5 in front. In the parentheses, I have 1.45. So the difference from 1 is 0.45 or 45%. And the last one, 4/3 is greater than 1, so this is growth. My initial value is the 3 in front. In the parentheses is 4/3. The difference from 1 is 0.3 repeating, or 1/3. So that's 0.3 repeating, so this is 33.3%, or 33%. Number 2, run an exponential model for each situation. Use the variable t for time. In 2001, 600 million computers were in use. The number of computers C increased by 10% per year. So my exponential function is y is equal to my initial amount is 600. Oop, drop to 0. 600 million. Now I could just write the word million or just say in millions. The number of computers increased by 1% per year. So this is number of computers, C, increased by 10%. So 1 plus 0.10 per year. So we'll do T for years. Okay. Letter B. In 1963, there are 41 million acres of ponderosa pine forests. The number of forests, F, decreased by 0.5 per year until 2002. So I'm going to start with 41. Again, like I said earlier, I could say 41 million. So you could actually leave off the word and at the end just say in millions. 41 million acres. It decreased by 0.5%. So 0.5% is 0.005. But this is decreasing, so this is 1 minus 0.005. So this is 0.995 to the t power, because that's the number of years. The 1963 is my starting point, 2002 is my ending point, but neither of those actually show up in my equation. I forgot the equal sign. Letter C, you purchased a cell phone for $125. That's my starting value. The value of the cell phone C decreases 20% annually. So my initial value is 125. This is going to be 1 minus that 20%, so 0.2, which is 20%. So that's going to be 0.8. 0.8 annually is to the t power. Letter D, in 1983, 3,173,000 gas grills were shipped by various manufacturers. Shipments of grills, G, increased by 7% per year. So my shipments of grills, G, that's an ugly G, let's make a little nicer G, increased. So my initial value is 3,173,000 times 1 plus 0.07, or 1.07 to the t for t years. All right, that's going to be the end of this first video. The rest of this will be on the second video.